Heat flow thermodynamics. In almost any chemical process plant, materials are constantly being heated or cooled. This is done for a variety of reasons. As we have seen in the previous unit, it is often necessary to heat viscous materials in order to make them flow easily. Another reason for heating is to melt solids, or to change liquid into vapors by boiling them. Chemicals may be heated to increase the speed of a chemical reaction or to make it occur at all. A handy rule known to most chemical engineers is that a 10 Celsius increase in temperatures will approximately double the rate of most reactions. But some chemical reactions give off heat as they occur. Such material generally requires cooling if the reaction to be properly controlled. Cooling is also required to change or condense vapors into liquid and to freeze liquids into solid. In many reactions, the temperature influences the products being formed. Consequently, the temperature must be controlled so that the material remain at the temperature the process the highest yield of the most desired product. The science concerned with the generation and transfer of heat is called thermodynamics. The subject is emphasized in very chemical engineers education. In almost all chemical process plants, heat is generated by the burning of fossil fuels, coal, oil, or natural gas. The heat given off by the turning fuel may be used directly, but most often it is used to generate steam which is piped to the place where heat is needed. The easiest way of heating a liquid with steam is to bubble the steam directly into the liquid. For example, steam can be supplied to a pipe immersed in the liquid. A number of small holes are drilled in the pipe to allow the steam to escape in small bubbles. Such a device is called a sparger. The bubbles of steam rise up, transferring heat to the liquid and mixing it out at the same time. During this process, some or all of the steam condenses into water, which remains in the liquid being heated. Consequently, this kind of heating, called direct injection of steam, can be used only if the pressure of condensation water is not a problem. In most cases, direct injection of steam is impossible. The steam and the liquid to be heated must be kept separate. To heat the liquid without direct contact, a pipe of equipment called a heat exchanger is used. It has a barrier of some solid material between the heating medium and the material to be heated. Many varieties have been invented, but by far the most common type is the cell and tube heat exchanger. The material to be heated may be tube side passed through the tubes, with the steam cell side outside the tubes. It is possible to have steam on the tube side and the other materials on the cell side, but this is uncommon. Usually, the steam is on the cell side so that it condenses on the outside of the tubes. The resulting water falls to the bottom of the cell where it is allowed to pass out of the heat exchanger by means of a special device called a steam trap. This is designed to permit the escape of condensed water content from the steam while trapping the steam, preventing it from escaping. At normal atmospheric pressure, water boils at 212 Fahrenheit, 100 Celsius, or 100 Celsius, and its steam is at the same temperature. If the pressure is increased, the boiling point of the water and the temperature of the steam being produced rises. To use high-temperature steam, it is necessary to design and build all equipment to withstand the high pressure associated with the high temperatures. High-pressure equipment is expensive. Sometimes, to provide high temperatures without Without having to deal with high pressures, chemical engineers use special heat transfer liquid for heating. These are materials remain liquid much higher temperature than water. Two common heat transfer liquids are known as deuterium A and deuterium A. Deuterium is a trademark of the Dow chemical company, which manufactures and markets the product. Deuterium A is a mixture of two chemicals, diphenols and diphenols oxide. It boils at about 450 Fahrenheit or 230 Celsius. Deuterium E is dichlorobenzene, which boils at about 300 Fahrenheit or 130 Celsius. Some minerals oils are also sold for use as heating transfer liquid at temperatures ranging to about 600 Fahrenheit or 315 Celsius, but most tend to deteriorate if kept at high temperatures for a long time. The deuterium materials are very stable even after many years of use at high temperatures. If a material is to be cooled, a cell and tube heat exchanger can also be used. The cooling medium is normally water, chilled water, or cold brains. As mentioned earlier, brine, or a solution of salt in water, is used because it freezes at a lower temperature than pure water. Sometimes liquids are cooled by circulating them through pipes exposed to the atmosphere. This is called an air-cooled heat exchanger. The cooling process is speeded if a fan is used to blow cool air rapidly over the tubes. When a cell and tube heat exchanger is used for cooling, the material to be cooled may be either on the tube side or the cell side, with the cooling medium on the other side. If one, the two liquids is more corrosive than the other, brine, for example, can be corrosive. It is usually on the tube side. The tubes can then be made of corrosion-resistant materials with a cheaper materials for the cell. If a corrosive material is used on the cell side, it in contact with both the inner surface of the cell and the outer surface of the tubes. Both the tubes and cell must be able to withstand corrosion. It is possible to operate cell and tube heat exchangers is either in horizontal or vertical position, but horizontal exchangers are most common. When steam is used for heating, it is always introduced through the upper opening or nozzle in the cell so that the lower opening can be used for draining condensate. If a pool of condensate builds up in such an exchanger, usually due to multifunction or wrongly sized therm trap, and submerges some of the tubes, the heat transfer suffers because condensing steam transfers heat more rapidly than does hot water. When a liquid used to cell side, it is always introduced through the lower nozzle and withdrawn through the upper nozzle. In this way, the engineer can be assured the exchanger remains full, with liquid surrounding all the tubes. Cell and tube heat exchanger are so widely used that they are available as stock item for many manufacturers. There are a number of standard designs used through the industry. These are detailed in a publication of the Tubular Exchanger Manufacturer Association, or TIMA, and are therefore called the TIMA standard. However, no group of standard heat exchanger could fulfill all needs, so many exchangers are custom designed and manufactured. The size of the cell and tube exchanger needed for any particular job depends mainly on the amount of the heat to be transferred and the volume of fluid to be handled. The calculations are learned in college by most chemical engineers, but computer programs now do them automatically. Autonomous heating is done with steam heat or heat transfer liquids such as deuterium. Other liquids may also be used as the heating medium. This is most commonly done when there is one liquid stream is a plant that needs to be heated and another that needs to be cooled. Passing both streams through the same heat exchanger will accomplish both objectives simultaneously. When a heat exchanger is used with liquid on both the tube side and the slide side and the cell side, the two liquids are usually made it flow in opposite direction. This is known as current flow. If both materials flow in the same direction, the flow is called co-current. Sometimes a heat exchanger is designed to chill the vapors of a substance and condense it into a liquid. A special exchanger of this kind is called a condenser because of the way it's used, although it is not too different from any other heat exchanger. When used as condenser, cell and tube heat exchanger are often mounted vertically. When a fluid flows in a pipe, it moves faster at the center of the pipe and slow just at the wall because of friction between the pipe and the flowing fluid. When fluid flows relatively slowly, there can be a fairly thick layer of fluid near the pipe wall that hardly moves at all. This condition is known as laminar flow and makes for poor heat exchanger because the static layer of fluid near the wall acts as a resistance to the movement of heat. When fluid is flowing rapidly, swirls and eddies are set up that reduce the thickness of the static layer near the pipe wall and thereby decrease the resistance to the movement of heat or increase the rate of heat transfer. This kind of agitated flow is known as turbulent flow. The speed at which laminar flow changed to turbulent flow was investigated early in the currently by an experiment named Obstorny-Reynolds. He worked out a relationship known as the Reynolds number that helps to determine the transition from laminar to turbulent flow. The Reynolds number is found by multiplying the inside diameter of the pipe by the fluid velocity and the fluid density, and dividing by the fluid viscosity. The units used for the variables are selected so that all the units cancel out. Hence, the Reynolds number is known as dimensionless numbers. For example, diameter in centimeters, velocity in centimeters per second, density in grams per cubic centimeters, and viscosity in grams per centimeter second. When the Reynolds number is less than 2100, flow is always laminar. When it is above 4,000, flow is always turbulent. Between Reynolds number of 2,100 and 4,000, the flow may be either laminar or turbulent, depending on condition at the entrance of the pipe and on the distance downstream for the entrance. Thank you.